Okay, we want to move on to section 5.9. One thing I want to point out, and I meant to do this in 5.8, but I want to show you this simplified uh, representation of this series motor configuration. Yeah, what I wanted to show you, and I failed to point this out last time, was this, and you know, both of these representations of a series motor are useful, depending on what it is that we're trying to focus on. But what I wanted to show you with this is just look how simple that is, right? I mean, you talk about a simple circuit. This is showing us the series field here, producing the flux that we need to generate the armature voltage. And you can't get a more simple circuit than that, right? So that was one thing I wanted to point out to you. Now, the other thing that I wanted to point out to you, and I know this all kind of starts running together, and actually, I got an email that I love getting emails from you guys, lets me know that you're out there. But the person was talking about the number of equations and so forth that are in this. And what I would tell you is that, normally in the classroom, you would develop an equation sheet. And for this particular course, what we do is we develop an equation sheet for each chapter. And you always have access to that equation sheet. And, it's just better that way. There's other things we can memorize. I want you to focus on concepts and how things work, and then have access to the equations. But everything that we're talking about up to this point, it's not one equation. It's multiple. So here's the one equation where equation 3.5, the power of the motor is determined by the speed times the torque divided by 955. The speed of the motor is determined by the constant 60 times the source voltage divided by the number of conductors Z times the flux per pole. And then the torque of the motor is determined by equation 5.6. Now, equation 5.6, if you'll remember, is the one that's not labeled in your textbook. And it says that the torque produced by the motor is the Z times the flux per pole times the armature current. All right. So again, as that armature current increases, like at startup, we see the huge effect that has on the motor torque. So in section 5.9, he says, when the series motor's carrying a load and, it's operating, at normal conditions, we may need to vary the speed just a little bit. Now, one way that we can do that is we could place a resistor in parallel with this series field. Okay, so we could do a number like this. We could have a parallel connection to this field, and so we may shunt some of the current, through this parallel field. And what's going to happen with that? Well, let's look at our equation and see if we can figure that out. The first off, if some of that current is removed from the field, it's going to cause this to go down, which would cause the speed to go up, right? And so, we can see the relationships. We can also explore the relationship that might have on the torque, right? So if the armature current decreases slightly, or this goes down, it's going to cause the torque to go down. But we were talking specifically here about the effect that parallel resistor added to a series field has on the speed, right? So we can obviously see what that would do. And then he tells us also that sometimes the speed may be lowered by connecting an external resistor in series with the armature in the field. So it would be like another series resistor already with this series field. And what would happen then is that this would cause an IR drop, right? V equals IR. This would cause an IR drop across the resistor and the field reduces the armature supply voltage. So E sub S would fall. So if E sub S falls, the speed would fall. Okay. So anyway, those are a couple of ways that you can change the series motor speed. We call that series motor speed control. And then again, you know, this is what I would want you to recognize, you know, immediately is this is representing a series motor configuration. And, you know, we can tell that by the shapes of the curves, and we can see that very large starting torque here. And we see the torque goes down, right? The torque goes down as the speed increases. And we would think that to be the case, right? Because of this equation here. Okay, so, and this equation too. So anyway, let me stop it there and then we'll work example 5.5 in a separate video.